Good afternoon, everybody. My name is Mark Schellhammer. I'm the MC for today's event. First of all, I want to apologize a little bit. I'm actually reading my notes here for this presentation because I have a fair amount of material to cover before I introduce our speakers, and I want to make sure I get to everything accurately. I direct something called the Human Spaceflight Lab here at Johns Hopkins University School of Medicine, and a program we call Bioastronautics at Hopkins that aims to promote human spaceflight, not only here, but at other universities and institutions as well. And this symposium, Mini-Symposium today, is one of the Bioastronautics at Hopkins outreach events. This is part of a larger umbrella group overall at Johns Hopkins that's called Space at Hopkins. Our efforts here are supported by the Office of Research and Translation in the School of Engineering. And today's event is actually run by our partners, Hopkins at Home, which provide video and online promotion and production. Now, before we talk specifically about today's event, I want to start with a brief dedication. There are two people in the bioastronautics field who have had a huge influence over the years in my own professional life and in the lives of many others, with their mentoring, their leadership, and their research. One is my thesis advisor, Larry Young, a longtime MIT faculty member who was principal investigator on a number of spaceflight experiments, among many other accomplishments. He died in August of last year. The other is John Charles, the chief scientist of the NASA Human Research Program before I was the chief scientist, and then again after I was the chief scientist. I used to like to say that John didn't get it right the first time, so they gave him another chance after I was the chief scientist. But in matter of fact, I learned a tremendous amount from watching John perform that job, and he was a great mentor to me. John served many other roles over 35 years at NASA before retiring, starting as a researcher in the cardiovascular lab, mission scientist for 2 shuttle missions, including John Glenn's return to flight to space, played a key role in the NASA twin study. He died on January 17th of this year while serving as scientist in residence at Space Center Houston. So without these two gentlemen and their contributions, many of us would not be here today to have this discussion. Now, in February of last year, we held our first public event from the Bioastronautics at Hopkins initiative, a virtual half-day symposium covering a number of topics related to human spaceflight. November of last year, we had our first mini-symposium in which we focused on a specific topic, and that topic was systems medicine in human spaceflight. And those talks are recorded and available online. Today is our second mini-symposium on the topic of statistical approaches to human spaceflight data. We'll have presentations from 2 experts in this field, some discussion between them moderated by me, and then questions from the audience. You can submit written questions online during the presentations. They will then be read to the panel by Nabila Ali, and she's assisted by Malika Sarma and Linda McLean, who are off camera today. So you might ask why we're dedicating an entire program, a 2-hour symposium, to statistics. Does anybody really care about statistics besides biostatisticians? Isn't it just a necessary evil in order to satisfy grant and manuscript reviewers of science that we already know is valid and worth doing? Well, I would say no, even as a researcher, not a professional statistician myself. I'm one of the enlightened ones, let's say. I definitely see the value in statistics, and in part by working with our 2 speakers today, have really taught me how to look at data in a new way with new statistical approaches. The spaceflight research community is working hard to come up with solutions to the major problems that plague humans in space. This includes bone loss, sensory motor decrements, cognitive challenges, and a host of others. The research findings that they come up with will inform countermeasures and interventions that will make it possible to explore the moon and Mars. Astronauts' lives depend on these results. This research would be challenging enough in a ground laboratory or clinical study, but spaceflight presents additional unique challenges. The subject populations are small, experimental conditions are often poorly controlled, There may be environmental, operational, or medical confounds that we don't know about. This situation is improving, but in the meantime, there are existing data sets that can be mined for insights and new approaches that can be applied to new and ongoing studies. There's no point in pretending that we can design a standard laboratory study or clinical trial with standard conventional statistical guidelines under these circumstances, but we can be realistic and realize that there are some difficulties that we can't overcome, and spaceflight data are much too valuable to ignore just because they might not meet some of these conventional statistical standards, large data size, for example. So we have some guiding questions. For example, what can we do with existing data sets using modern methods to extract meaningful information from meager data? And how can we properly design flight experiments that take into consideration the logistical and operational constraints that are a reality in spaceflight? Our speakers for today have a wealth of experience in statistical approaches to, let's say, problematic data sets like the ones we get from spaceflight, human spaceflight data. So I will introduce our speakers in order, the order that they will speak. Our first speaker is Rob Ploutz-Snyder. Dr. Ploutz-Snyder is a research professor and assistant dean for research at the University of Michigan School of Nursing, where he also directs their Applied Biostatistics Laboratory and Data Management Core. Prior to that, he was a senior research scientist in the Biostatistics Lab in the Human Research Program at Johnson Space Center, where I met him. And prior to that, he was an associate professor of medicine at SUNY Upstate Medical University. He has over 20 years experience in applied biostatistics, working collaboratively with experts across many disciplines. He likes to say that he was a team scientist before the term became popular, as his most rewarding work has been in collaborative teams. Rob was one of the people who pushed me to get biostatisticians on NASA Human Research Program grant review panels several years ago. And he was a great help to me in making the case for more one-year missions to the International Space Station, a work that is still in progress 8 years later, but learned a tremendous amount from doing those tasks with Rob. So he will speak first in just a minute, but I'll go ahead and introduce Rob Reynolds, who is our second speaker, so I don't have to interrupt the flow later. Rob Reynolds is consulting research scientist and director of research for Mortality Research and Consulting Incorporated, which has to be one of the more interesting names for a commercial entity. Rob has a doctoral degree in public health from the University of Texas Health Science Center at Houston, with a major in epidemiology, minors in biostatistics and environmental and occupational health. Also has a master's degree in statistics from Texas A&M, and is, like Dr. Ploutz-Snyder, professionally accredited by the American Statistical Association. His interests include contemporary analytic approaches such as statistical learning, machine learning, and deep learning. I could go on, but what's most interesting for our purposes today is that Dr. Reynolds has an unusual knack for digging into sparse data sets from space flights, eking out conclusions and trends that might have gone unnoticed. Again, what I said a few minutes ago, these data are much too valuable and have been obtained at a much too high a cost to let them languish in a database somewhere. These speakers bring both theoretical and practical understanding to human spaceflight. I've had the pleasure of working with them both. It's always an amazing learning experience to see how they think about data and how they approach spaceflight data. It's more than doing a correct t-test, I can guarantee you that. It's an honor for me to work with them and an honor for me to have them here today to speak to you. Rob Ploutz-Snyder, the floor is yours.
Thank you for that kind introduction, Mark. Yeah, it sounds like we've got a great lineup today. I can't wait to put it all together for you. So the title of my talk is going to bring in some of the recent sort of larger debates about p-values beyond NASA, but then also to tie it to NASA research, because we have some particular vexing issues, including small n, but also some other issues that Dr. Shellhammer kind of hinted towards. So I'm going to go ahead and get right into it. So with NASA, we have small n and related problems in our human research. I'm going to mostly focus on our human research program. And if you're new to this, I mean, some of the issues, they sort of pop right out as soon as you start doing this. For one, spaceflight research on humans is almost always going to involve a very small sample size. There's a lot of great reasons for this, but there's not a whole lot of astronauts that are flying around at any given time, maximum of 6 on ISS. Usually only half or so are United States or in our consortium for data sharing. So we just have very few people, very few opportunities to collect data on them. ISS missions are long now, they're 6 months to a year, and most human research that happens with astronauts includes a section of data that's collected before flight, then during flight, then after flight. So even if you're lucky enough to recruit some astronauts, it takes a really long time to get data from them. So when you stack this up to try to get 6, 8, 10, 12 subjects, it can take a really, really long time. Now you might think, okay, so I'll just use spaceflight analogs, and there are many great analogs to choose from, but it actually turns out that they're not a simple solution either. Some of our best analogs are also very expensive to conduct, bed rest being a great example. It takes a long time for those data to be collected and used in a systematic way. And analog subjects, people who sign up to become research subjects, may or may not be good surrogates for astronauts. So there's certain limitations to that data as well. And the trouble is that NASA needs answers faster than our current throughput can provide. So even if you get a grant funded for a study, there's a really good chance that the sample size that you're going to have access to is smaller than you want it to. So it's a pretty global problem for all NASA human research. But before I get into NASA, I want to sort of take a step back and talk about science in general, and in particular, this big p-value and reproducibility issue. If you've been following the research on this, there's a pretty robust history now of identifying that statistics in particular and the hypothesis testing procedure is not producing the most reliable science that we once thought it should be. And back in 2014, Nature published a really nice piece on this. I encourage you to pick this one up if you can. It's pretty compelling, but it's striking hard at p-values as the gold standard, suggesting that perhaps we need to take some alternative approaches than just focusing on p-values. Later in 2015, actually, I think partly driven by that first Nature article, there was another journal in the social sciences that actually banned the use of p-values in any manuscript. You can't even have significant p-values and asterisks in those manuscripts. So this was a pretty harsh endorsement of the issue of p-values. I don't know how many other journals have followed suit, but as far as I know, this journal still does not allow scientists to report statistical significance levels. So they're forcing contributors to think about science differently. That was in 2015, and shortly after that, in 2016, the American Statistical Association released a position paper on significance testing and p-values. And you may not be an ASA member, but I will tell you that ASA rarely comes out with position statements. So for them to take a position statement that was this strong, challenging science all over across disciplines to really rethink our over-reliance on p-values, that was a big deal. ASA just doesn't release these position statements often enough, but the evidence was compelling and arguing that we really need to rethink this over-reliance on p-values. Now, this paper, when it came out, you might think, oh, this obscure American Statistical Association paper, no one's going to read that stuff. But it was a huge splash, over 150,000 views since I created these slides a year or so ago. I'm sure it's probably 200,000 or so by now. So this is not an obscure piece that's tucked away in a journal that nobody ever reads. It was widely reviewed. And then shortly after that, Nature published yet another piece on reproducibility and some of the flaws in science, where they interviewed 1,500 or so high-level scientists. I'm not talking about brand new, newly minted PhDs, highly productive scientists, well-funded researchers. And they basically gave us a quiz about how well we understand p-values and hypothesis testing and the whole scientific process. And it was really quite compelling because in this paper, while more than 70% of these researchers tried to reproduce their own or other scientists' results, 70% of them failed. And yet still, the large majority of them believed in and still trusted the published literature, even though it was not reproducible. Now, jumping back to that ASA position paper, just to sort of drive home the fact that it wasn't this obscure thing that was never seen by anybody, there's different ways that you can evaluate the impact of a publication, and altmetric scores are one of them. And this particular piece, their altmetric score was in the top 5% of everything that was published that year, the top 5% from a stats journal. I really had to smile when I heard that, because most people don't think of my field as having, this wide of an impact, but it surely did. And there's other ways that you can measure impact of a publication too. This is the dimension score, the Google metric. And the graph on the upper right shows the number of citations by year. This piece was cited over 2,400 times. And not just in math journals either, or statistics journal. It was cited all over the place. I'll give you a representation of that in just a minute. The other statistic that I really like to draw your attention to is what's called the FCR, the field citation ratio. And this is a metric of how many times this particular paper has been cited in its discipline and in its year relative to other papers that were also published that year. And if you had an FCR score of 1, that means that your paper was published or was referenced on average, just like every other paper that year. If you had an FCR score of 2, that means that twice as many references to your paper are occurring than the average paper number that year. This thing had an FCR of over 1,200. So not only is it being read a lot, it's being cited a lot. People are aware that this is happening. And so, it was hugely popular, but why? Why was this such a big thing across disciplines? Well, I referenced back to that Nature piece where over 50% of the scientists that were polled there believed that we were in a crisis of reproducibility. They believed that they couldn't reproduce their own work, let alone that of other people in other labs. And the primary tool that we're using in scientific inquiry is hypothesis testing. So, that does point a giant flashing arrow to p-values and our reliance on those methods. And I'll add too that with big data, this exacerbates the problem more, or even just large secondary data sets where there's a tremendous amount of statistics going on. And then of course, NASA has this vexing issue of small samples, which only makes the p-value problem harder to deal with. So what's the trouble with p-values, regardless of your sample size? Well, it's been shown over and over again, that Nature piece, I keep referring back to it, please read it, you'll be impressed. We don't understand p-values as a discipline, across disciplines. We often misunderstand what they mean. We'll analyze data, get some significant results, and then try to interpret those results. That is the acronym of p-harking, or hypothesizing after the results are known. Exactly not what you're supposed to do with the frequentist hypothesis testing approach. We oversimplify, we dichotomize the decision about whether an effect is important or not, indicated by significance. And this problem isn't going away because we're teaching these same methods to our new students, our funding agencies, our journal editors, our mentors, our curriculums. They're all built around this. And so they're perpetuating the problem. It's not going away without a really concerted effort to start to make things change. And as I mentioned earlier, big data and large secondary data sets now are pretty commonplace, and these are presenting even more challenges. So this is a serious problem. It's not going away fast. What should we be doing about this? Some of the common misconceptions we have, I have listed here. I won't read them all off because I am limited in time. But if this was my full-length talk on this issue, I often give quizzes to people, true or false, on these kinds of things. And you'd be surprised at how many times you might get stumped. We misattribute what p-values mean all the time. We assume that p less than 0.05 supports the alternative hypothesis. It does not. It could support many alternative hypotheses. The flip side is if we have a p greater than 0.05, could be supporting lots of different null hypotheses. There's confusion about our terminology, what we call chance probability, as opposed to other types of probability. We often equate p-values to effect sizes and importance, which it clearly isn't. And so there's a tremendous amount of confusion, even among top scientists and even newly minted PhDs. So you might think, let's get away from p-values and go to confidence intervals. And I think you're on the right track with that thinking. But unfortunately, We don't understand confidence intervals all that much better either. There's a lot of confusion about what a confidence interval represents, what it means, and what it doesn't mean. So just avoiding p-values and jumping over to the confidence interval language is not likely to solve this problem because we don't understand that much better. So this was in March 2016. The ASA released this statement saying that the p-value was never intended to be a substitute for scientific reasoning, and that well-reasoned statistical arguments contain much more than just the value of that single number, and more importantly, whether or not it exceeds some arbitrary threshold. And in 2016, this paper was intended to steer people to think beyond p less than 0.05 and to just use their scientific minds in a more meaningful way. And we advocated for 6 different principles that people should be doing with the research. I've listed them here. P-values can indicate how incompatible the data are with a specific statistical model. They do not measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone. That's a common misconception. We're reminding folks that scientific conclusions should not be based only on whether a p-value exceeds some specific threshold, let alone the one and only threshold that you ever hear about, 0.05. That proper inference requires full reporting and transparency. The 5th principle, that p-values or statistical significance doesn't measure the size of the effect or the importance of a result. So you can have a small p-value associated with a big effect and a big p-value associated with a small effect. They don't go hand in hand. And they don't, in and of itself, they're not deserving of a good measure of evidence. So with these 6 principles in mind, back in 2016, I think a lot of statisticians were hoping this would get a lot of exposure. It did get a lot of exposure, but what happened from that exposure? Well, there's additional text as well that was helping scientists, giving you that, I mean, you could actually cite this in your grant proposals and in your manuscripts, helping folks to understand that now they have some real solid legs to stand on, as so, you know, pushing for effect sizes in addition to or even instead of p-values, considering alternative methods like Bayesian methods, decision-making or decision theory, considering things like false discovery rates instead of family-wise error rates. So it was widely viewed, it was highly cited, but what really happened, I would say, a lot of nothing. Has it altered the way you're publishing your work? Have you stopped seeing p-values being reported in the literature since 2016? Are you reviewing manuscripts any differently? Probably not. And this was way back in 2016. So in 2019, a few years later, the ASA come out again with a big position paper and an entire issue, an entire journal dedicated to what they called moving beyond the world of p less than 0.05. You know, it was almost like we came out and said, look, you didn't listen to us into 2016, so now we're going to get serious. And in 2019, the ASA now came out and formally said that based on our review of the articles in this particular issue and the broader literature, it is time to stop using the term statistically significant entirely. Nor should variance such as statistically or significantly different, p less than 0.05, non-significant, none of that should survive. This is a statement by the American Statistics Association. Let that sink in just for a moment. The ASA is telling us we should stop using the phrase statistically significant because we've been doing it wrong for so many years and we haven't been listening to the warnings. Have you stopped using that term? I bet not. Most people haven't. So what should we be doing? Well, the first thing I'm going to suggest to you, I don't have time to go through the entire journal with you, but I think you really need to look this one up. I've provided a link in my slides. I'm sure this will get shared afterwards, and read this whole issue. I want to encourage you to read it. It is not intended for statisticians. It is easily approachable by any various discipline scientists. It's not just this one paper either. There's 40 some short articles written in addition to that, plus a bunch of others that were added online too. I say 22 here, but I bet it's probably double that by now. Now, there was 3 overall principles in this piece, trying to encourage people on what to do. One was to accept uncertainty, not pretend that statistics provide a certainty, but accept uncertainty, be thoughtful and be open. Just a little bit more detail in terms of accepting uncertainty. We really need to recognize that statistics don't get rid of uncertainty. And in fact, it quantifies the level of uncertainty. We need to get rid of this binary decision. It's significant or it's not significant. Anything less than 0.05 is an important effect that deserves publication. And if it's 0.051 or greater, we shouldn't publish it. That's a fallacy. We need to get rid of that thinking. And to think of different ways instead to quantify, to visualize, to interpret the effects that we do observe based on effect size. In terms of being thoughtful in your approach, we need to be thinking about the practical implications of an effect, regardless of its significance value. There's a quote that I like to say often is, in order for there to be a difference, it has to make a difference. I wish I knew the original author. I don't. If somebody does, please send me the author for that. But that's a big one, right? If it's not practically significant, then we probably shouldn't be talking about it. And if it is, we probably should be talking about it, whatever the p-value. How precise is our estimate? We know, particularly with small n, that we're going to get beta coefficients or average deltas or whatever it is, but we know that there's error around that. So we need to be talking about the precision. And also, is our model and all of the components leading up to our model specified correctly? Additional, in terms of statistics, the ASA is advocating that you consider alternatives to p-values. In fact, they don't want you to report statistically significant. Whether or not that's practical is another issue. But some of the ideas that are put forth are things like consider multiple null distributions, not just one. And also, one of the ideas I really like is rescaling p-values into something that makes more sense. We've already shown that people don't understand p-values. So why don't we rescale it into a new metric? One of the ones I really like a lot is the Shannon information criteria. Some people call this the surprise index. And basically, you can take any p-value from your research, take the log base 2 of that p-value, and you get a Shannon information criteria. And the example I give is if I were to toss a coin, a fair coin, 5 times in a row, and come up with heads 5 times in a row, you might think, oh, that's unusual. Is that a bias coin, or is that just a fluke? 5 times in a row, that's a lot. 5 times in a row equates to a p-value of around 0.034. And so you can use that information criteria to say, this is the sort of surprise index associated with observing my data if the null hypothesis or null hypotheses are correct. Now, what if I flipped the coin 10 times and got 10 heads in a row? That equates to a p-value of 0.001. But see, once you understand the Shannon information criteria, you're basically saying, how surprising is that? You're not saying it's yes or no, it's just how surprising is that? There are other suggestions in this paper that I don't really have time to go into, but my slides talk about some of these other approaches about being thoughtful. In terms of communications, I'm advocating, I still report p-values, I admit, because I work in science and medicine, and if I didn't, I couldn't get published. But I have an absolute resolute focus on effect size and also on precision in all of my publications and grant proposals. And I'm also going to suggest, in terms of confidence intervals, that you get rid of that word confidence and you replace it with compatibility, because I think that will help us understand what a compatibility interval is. It's how compatible are our data with the null hypothesis. So instead of confidence, maybe compatibility will help you with language in terms of communications. The ASA is also advocating for some other steps to be open about our research. Things like pre-registering of your methods. If you do any clinical trials, you're familiar with this. Sharing your data and your code. Some journals are now requiring this, and I think that's a great idea. I love the idea of acknowledging expert judgment, so we don't have to just have statistics just telling our story, but also they're advocating that journals feature a replicated by sort of almost like a certification. So you submit your journal, you submit your article, your data, your code, and you allow it to be replicated by somebody else entirely. They now have your data, they have your code, but they're probably going to do their own code to see if they can essentially replicate the results. And if they can, you get this sort of certification, if you will. It's a reproducibility evidence. So the other aspect, I think the ASA is not naive. We realize people are still going to report p-values, but instead of calling it less than or not less than some critical value, just report what it is, because it's a continuously scaled thing. So why not show what it is? And then also interpret it in the context of sample size. This brings me back to NASA, because NASA is no different than any other science. We suffer all of these same reproducibility in these other issues, but we also have another problem, and that almost all of our research is small n. So give up the idea of any sort of subgroup analysis. You'll be lucky if you can get valid primary analyses. So with small n, we struggle, in addition, to find publication outlets. We can often not get our work published outside of the very narrow focus of spaceflight research. We can almost never achieve the obligatory power that would be necessary for a typical grant. So we have to think about justifying sample size differently. And relying on something as simple solution like confidence intervals is not going to solve the problem either, because with small n, we're going to have super wide confidence intervals, right? It doesn't go away. So, and NASA researchers face, unfortunately, other problems, in that we can't do the nice, pristine, controlled clinical trial that we'd like to do. We usually don't, for instance, have a control group. Astronauts get pitched various studies. If they decide to enroll in your study, then they do. We don't have the luxury of now randomizing half of the astronauts to your study and half of the astronauts to a control group. We just don't have that luxury. So we usually don't even have a control group. And even if we did, it would be a self-selected control group, because astronauts choose or not choose to be in your study, and they have to be fully informed. So it's a little different than a regular RCT. We're often mixing equipment too. The stuff that we take measurements on Earth is different than the equipment that we have available to us on ISS. So that adds additional error to the metric. We have mission constraints that always interfere. The example I give is if your data was supposed to be collected on this day at this time, but the toilet breaks down, guess what they're going to be working on? They're not going to be working on your research. They're going to be fixing that toilet. There's a lot of missing data problems as well. So we have all of these other contextual problems facing us with our research. How does that impact the p-value debate? Well, when you realize that the whole hypothesis testing with the frequentist methods assumes that you're doing this with all of the assumptions of the whole statistical model, not just of that statistical test, being met, you often don't meet many of those assumptions. So already now the p-value problem is even compounded further. Now we can reduce some of these problems by really being careful about choosing outcomes that maximize the signal to noise ratio. We can involve our crew in the pre and the post-flight data collection, since they're going to be the ones collecting the in-flight collection. That seems like a natural thing, but it's often not done. We can start to perhaps randomize to condition, but I will say I don't think it's practical for the current state of spaceflight. We can try to reduce missing data or use multiple imputation when it's feasible, but I think that's going to be tricky as well. I'd love to say run larger studies, but I think that's going to be limited to analogs. So some of the more practical consideration, when you learn statistics in your discipline, we always teach, the various assumptions that go with the statistical test. And we want you to test those assumptions, but then we quickly get on to the next test and we say things like, don't worry, this test is robust to violations of assumptions. That's not true with small n. It has never been more important to test and meet those assumptions. And then if you don't meet them, choose some alternative, usually non-parametric methods to analyze your data. Repeated measures designs are great, but there's assumptions there that have to be met too. So my point of this slide is to say assumptions, 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 test them and make adjustments. Challenge the default. It was never intended to be the case that there's only one alpha that matters, that only two tests matter. There are papers out there. There's one called the optimal alpha that I really like, that forces the PI to weigh type 1 error risk and what that means versus type 2 error risk. I really love that paper because it forces you to think that through systematically and then adjust it after you got your data. So there are some of these things out there. In terms of fighting for grant dollars, when you have to do a power analysis, I'm shifting all of these small n's now when I do power analysis to precision or value of information theory. There's some of this information out there now, and I've provided some links and some references. Some statistical considerations that are small n friendly while focusing on effect size and things that are clinically or scientifically meaningful. Testing the contributions of blocks of predictors in a multi-predictor model instead of just one at a time. That's really helpful for small n. Using mixed effects modeling helps a little bit with longitudinal data, but also I think you just need to think more broadly, and our other presenter today is going to have some great ideas about this. But there are different experimental designs that are now commonplace, and maybe you weren't exposed to them when you were taking your training, like N of 1 designs or adaptive trial designs. Start to think about these things because they can be way more efficient for small samples. Now, there is a sort of silver lining around this. I'm really actually happy that the ASA has come forward so forcefully acknowledging that there's this p-value dilemma across the board, because now NASA researchers aren't alone, right? Mainstream science is recognizing this. Even more directly, the NASA Research Administration knows about this, and they've already started to build in an acknowledgement of the problems of small n and p-values. And we also have a journal now from Nature dedicated to microgravity. And I know that the editors of that journal are very sympathetic to small n and p-value issues. So that's the sort of silver lining to this. When you get my slides, you'll see there's a whole bunch of different references that I'm providing to you, not because I want to impress you with all the reading that I've done, but that I want to give you these tools because I think and I hope that these will give you some shoulders to stand on when you're proposing these sort of groundbreaking approaches to statistical analysis that go against the curve, against the dogma, but you now have many resources to cite to help justify that. With that, I'm going to hand it over now. I hope I stayed pretty close to on track for my time, and then I'll be happy to entertain questions later.
Robert, that was excellent. Thank you. So before I turn it over to Rob Reynolds, I'm going to take the chair's prerogative to ask you one question. And of course, there'll be time for further discussion and questions later. But one comes to mind immediately. If this is such a lousy approach, how did it rise to take center stage like it has? Why is there so much reliance on p-values, significance, and all the gradations? Is it something as simple as just that people don't want to think about it? A corollary to the idea that a scientist would prefer to just go do the science, and at the last minute, you bring the statistician in to do the statistics, and it just give me the answer. Yeah, we're done here. Is it just that people don't want to think it through, and this provides a way to avoid thinking so they can get on with the science?
I think you hit on both of the sort of root causes. One is we're cognitive misers, right? And as content experts, we have deep, deep, deep knowledge about our content area. And that's what we want to think about. And for a long time in science, you know, if you look way back, you know, most papers were authored by one PI and maybe two, or even three co-investigators. Nowadays, there's whole teams involved. But science kind of evolved from sort of a, you know, the one-horse show to small teams. And I think oftentimes statisticians weren't brought into the fold. So a lot of content experts were doing their own deal. It's not so much the case now, but we've had this inertia of just adopting these rules of thumb as if they were fact, when really they were never intended to be that way. If you look back at some of Fisher's really early work, he never advocated that 0.05 be the only p-value. And in fact, I can't get the words exactly. The acknowledgement was if you have no other way to justify your significance, then maybe 0.05 is something good to consider. But all along, it was thought that you would think these through critically each time you did studies.
Yeah, I've
a life of its own.
Yeah, I've read that too, and I agree. I was shocked when I saw that one of the statisticians who was cited frequently as one of the people who laid the foundation for all of this standard hypothesis testing approach, kind of railing in advance against becoming overly reliant on it. It reminds me a bit of the researchers' relationships to the statisticians. I think has a parallel to the researchers' relationships to the IRB. So those of you who do human subjects research know exactly what I'm talking about. And for a long time, it was like a necessary evil, right? You think you form your research, you create your proposal, you put your protocol together, you get everything in place. And then at the end, you think, oh, now I have to get this past the IRB. What a pain. I wish I didn't have to do this, but let's do this. Similar thinking on the after the study is actually performed, I think has been prevalent, if not unanimous, with statisticians. I'll do all the science, I'll bring in the statistician at the end. In both cases, especially as science gets more, research gets more complicated, in both cases, I think those are passé, dramatically so. I have come to realize that the IRB, I have to grudgingly admit, the IRB can be my friend because they will make me think of things that I would not otherwise think of in the planning stage of a project. So embrace that. It's okay, it's additional work, but it will actually help the science. Some of it is turning the crank, but some of it helps the science. And I think the same with bringing statisticians in at a relatively early stage will definitely help you think about issues of precision, reliability, consistency, experimental design more broadly, and not just making sure you get enough data points on enough people to do a power analysis and a t-test. So, all right, excuse me for going on and on like that. Thank you again, Rob. We'll hear more from you later when we get to the discussion section. And now I'll turn it over to our second speaker, whom I have already introduced, Rob Reynolds.
Thank you, Mark. Good afternoon, everyone. I'm Rob Reynolds. After the excellent introduction there by Rob P.S., I'm here to talk to you about some other alternative analytics for your spaceflight data. A little bit about my background beyond what Mark told you in the beginning. This is kind of a collection of places that have either given me degrees or paychecks over the years. And the reason I want to show you this is just that part of what's formed my viewpoint on all of this is a broad diversity of research that I've participated in and things I've had to think about, and more importantly, problems I've had to solve in situations small and large. As far as an academic career, I started out with a bachelor's in psychology, moved into public health and statistics, and then sort of did self-study in data science and machine learning. And you're going to see some of that today, I think. And this has given me this broad base of experience that I hope to draw upon and impress upon you, that you can free yourself from some of the misconceptions that Rob outlined in his talk. So we'll start with a bold assertion today, and that is that NHST, or null hypothesis statistical testing, is a prison of the mind. What do I mean by that? Well, to me, a prison of the mind is any self-imposed and needlessly self-limiting belief structure. And the reason I think NHST fits this is that it, first of all, is self-imposed. We do it because we think it's the right thing to do, and we think it's what other people want us to do. But that trapping part of it is what it does to our research. It warps our study design. In the experiments, we see this in the fact that we sort of back our way into how big we want our study to be based only on these type 1 and type 2 error considerations. In observational studies, we can actually give up and not do research we probably should do because we say, well, we don't have the sample size to paint ourselves into that type 1 and type 2 corner that we like. And then in both of these situations, we can distort some of what we're actually looking at and how we try to answer our questions, because we're always looking for that, where's my beta equals 0 H naught? Or maybe my beta 2 minus beta 1 equals 0 H naught. So it tends to make us lose sight of what we really want to know because we're trying to squeeze it into that NHST paradigm. And from my perspective, there's far more important ways you can get it wrong. Two of which are listed right here: confounding by indication, which Rob touched on a little bit. This idea that these exposures, whether it be space flight or some kind of chemical agent and occupational exposure or what have you, are not random. This isn't a controlled trial. People get these exposures for a reason, and that may be also related to whether or not they get the disease you're looking at or the problem. My favorite by far is what's tongue-in-cheek called errors of the third kind, or the type 3 error, which is answering the wrong question. And I think we'll see a little bit of that as well. So what are some potential alternatives? It's great to call out all the problems, but what do I do differently? I think of them in terms of two broad categories here. The first is realigning epistemology. And if you're an armchair philosopher like me, you recognize that epistemology is the study of how we know what we think we know. So in other words, what we count as evidence needs to be different, and we need to think differently around our whole problem space. The first way for me to do that is to go back to some of the basics of epidemiology when it was a young science in the late 50s and early 60s. Sir Austin Bradford Hill, if you're not familiar with him, he and Sir Richard Dahl, both knighted for their work in epidemiology, were two of the pivotal figures in demonstrating that smoking was really bad for you. And so he gave this address back in the 60s where he talked about some of the causal guidelines that he uses when he thinks, or used past tense, when he thought about whether or not an exposure was causative of a disease. And he outlined 9 of these principles, and you can find them quite easily. I encourage you to go back and review those, because they're really logical tenets about the relationships between variables that we would expect to see if things are truly causal. And when we're talking about the spaceflight data, that's what we're interested in, ultimately, is the causal relationships. Because our quest for countermeasures has to start with what causes what, and then how do we intervene upon that process to prevent the bad things and or encourage the good things. Moving past Sir A. Bradford Hill, then we have what's known as modern causal inference theory. And this started in the mid to late 80s in computer science, believe it or not. And it's been a very fruitful collaboration with biostatistics, economics, epidemiology, and some other fields. And the idea was, could we formalize mathematically the principles of causation so that we could use observational data to draw valid causal inferences and get valid causal estimates of effect? Now, with the small n environment of spaceflight, you may not actually be able to execute a lot of those methods, but I think there's a lot of value in understanding them, particularly the assumptions you have to make around them in order for them to work. These are assumptions that we've all been making anyways, we just kind of weren't conscious of it. And they've done the hard work of formalizing it for us so we can really think deeply about those assumptions when we approach our problems. And then alternative hypothesis formulations. There are other things out there besides that H-naught of beta equals 0. And I think the pharmaceutical industry has done a lot of good work here, thinking about things like equivalence testing and non-inferiority and the modus tollens, and just different ways to ask the question where you might squeeze out a little more statistical power or have a better time of demonstrating what it is you really want to know. Now, the second big category for me is this use of alternative analytics. Obviously, Bayesian methods rise to the top here, and Rob touched on those a little bit, but they allow you to do cool things like integrate what you think is already true mathematically with what you're observing in your data set, and that's through the use of a prior distribution. They also give you nifty things like the 95% not confidence interval, but credibility interval, where you can actually start to make probabilistic statements about how true you think your hypothesis is. And that's really what we want in a lot of cases. Beyond Bayesian, then, we also have uncommon uses of common statistical methods. By that, I mean a lot of those assumptions Rob was telling you to check can actually be used to your advantage, because if you see where you violate them or where they aren't true, you might learn something about what your data are trying to tell you. And I'll show you some of that here soon. Simulation can be a powerful tool. This is where we're looking for the boundaries of the possible by trying to set up what we think is an adequate model of the data generating mechanism, and then manipulating all the different inputs in all the ways possible to find the edges of the distribution, if you will, and maybe even the most probable values of the distributions. And then, of course, as a broad brush, data science and machine learning. Unfortunately, a lot of the machine learning techniques thrive on a lot of data. So many, many rows, many, many columns. And we don't tend to have that here. But I think there's value in borrowing from the unsupervised machine learning and maybe helping to clean up some noisy data and or combine small data sets in ways that you can use them better. Now, some of these things are colored blue here today because rather than carry on dryly about them, I want to show you some examples of things that I've done trying to answer some off-the-wall questions. And the things in blue are things that we're going to explicitly see. But most of these are in the background somewhere, at least in my thinking, if not on the slides. So the first example, and I'm going to say all of these today have to do with astronaut mortality, because that's what I research in my independent research outside of NASA. Been involved in some projects at NASA with physiology and some other more bread and butter issues, but for me, it's mortality. So I'm going to draw from the examples of papers I published or that I'm working on. So this first one is space radiation and astronaut mortality. And this is, space radiation is of interest to many people inside the space agencies and outside. One of the questions we might ask broadly is, have these historical doses of space radiation absorbed by astronauts increased their mortality rates? More colloquially, are we killing astronauts with radiation by sending them to space? If that were so, we should see it in two ways. It would be through cardiovascular disease and cancer, potentially other ways, but those would be the main ones. That's where scientists have very solid sort of theoretical, hypothetical mechanisms for how that could happen through mutagenesis and DNA damage in cancer, through the damage of endothelial tissues inside veins and arteries for CVD. We have this background, though, this prior knowledge of comparisons between astronauts and the general population of the US, between LSH controls, between professional athletes and astronauts, where we see pretty consistently that they're actually at lower risk of death from these causes. So when we think about this, we have to start at that point and say, all right, we know kind of going into this that they're better off than most everybody we've compared them to. So what are the exact challenges then that we face here? Of course, power issues. This is kind of the small N symposium today. So we don't have a lot of people, which means they didn't generate a lot of person years, and we don't necessarily have a lot of deaths from either of these two causes. We have a large potential for exposure misclassification when we talk about radiation. The first time anybody tried to answer this question was in 1993, using data through 1991. And at that point, when we were talking about at most maybe a 3-4 week mission to space, most of the astronauts had gotten more radiation from the medical scans preparing to send them to space than they actually achieved by being at space. So you can see how that might mix us up a bit. Since the ISS's inception, obviously, we're starting to get these longer stints. But again, as Rob pointed out, there's longer stints means fewer people. So it doesn't really help us too much. Then there's a large potential for confounding, just from things we may not even think about. And I could leave it to your imagination to imagine those things. One practical issue is that these data can be very difficult to come by. Last time I asked about them a few years ago, I was told essentially, yes, there's radiation dose badges for everybody who's ever been to space, and there's passive dosimetry on all the missions, but it's not necessarily been collated and put into an easy to use data set. So if you were to try to kick the ant mound at HRP and try to get these data out of the LSAH, it may be a whole lot of activity for not a lot of reward. So it would certainly be nice to have a way to get at this question without having to go to a lot of trouble. So one solution I thought of is ask a little bit of a different question. Let's ask a broad does it or has it question rather than a by how much. Because when people would think about the gold standard way to do this, they would want to get individual data on the astronauts, look at their radiation exposures, try to get some kind of dose response curve with the mortality rates. There's a lot of issues we just outlined why that may not work beyond just small n. So why don't we just try to see if there's any signal at all? Is this worth getting all the really good data and going to all the trouble? So one way we might do that is using this alternative hypothesis formulation with modus tollens. This is also called contrapositive logic. And you can see in this left-hand column, the formal logical construction of it. It's this, if P, then Q. So if we see some event P, that means event Q will follow it. So if we didn't see Q, then we know P didn't happen. And one of the classic examples of this is if the lawn is wet in the morning, it means either that it rained or the sprinkler one was on. And if the lawn isn't wet, then it neither rained nor the sprinkler was on, type of thing. We transpose this to our current context, that's the right-hand column. So if doses of radiation absorbed by astronauts in space are sufficient to increase mortality rates from both of these causes, then those things are not. So yeah, make sure I get this right because it can be tricky. If the radiation is sufficient to increase both causes of death, then those survival curves would not be statistically independent. And if they are independent, then there's been no cause that could increase both those mortality rates. I'll show you how this goes. It's a little tricky in the word form, but we'll see. Operationalizing it then to statistical methods we know and love. There's a couple of different ways to draw a Kaplan-Meier curve. The first is what we might call the naive method. And that's just if I'm drawing one for cardiovascular disease, if somebody died of cancer, I'm going to censor it as though it's not important and just say, okay, their follow-up ends there without an event. If there's interference, I can use a method called cause-specific Kaplan-Meier curves or cause-specific survival curves, and then you'll see the bias because the curve will change shape. So let's take a look at this, because if we can compare them and it doesn't change shape, that's our evidence that there's no common cause there, because it's showing that they're statistically independent causes of death. So here I've done this for 4 different broad categories. We have our cancer and CVD along the top, all the other reasons you could die of natural causes there in the lower left, and then all the external causes in the lower right. External would be things like car accidents, motorcycle wrecks, spacecraft accidents, things that are truly lightning bolts that could happen to anybody in our astronaut cohort. In each of these plots, though it may be difficult to see at first, there's actually 2 curves. The solid color is the cause-specific, the one that corrects for bias, and the dashed is the naive approach. The reason it's difficult to see two curves is that they almost perfectly overlap, which tells us that the lack of divergence in these curves means that that's cause-specific approach is not correcting any apparent bias, which tells us that all these causes of death do not interfere with each other, which in the logic of causation tells us they have no common ancestor. So this is some evidence, at least, that the radiation they've absorbed thus far is not enough to cause them to have elevated mortality from both of these causes simultaneously. And so that's a limitation in what we can conclude here. We can see that, yeah, there's no common causes of death, but it means one of several possibilities emerge. It means that it's either not enough to raise either of them, or it's raised one and not the other. Nonetheless, combining this with our pre-contextual knowledge that these astronauts are typically at much lower risk than the general population and professional athletes and so on, makes me at least lean towards the idea that they've probably not had any sort of detrimental radiation dose to date. And it could change with one-year emissions and whatnot, but up to the point that this was done, didn't seem like there's any extra harm coming from radiation. The next example would be smoking and astronaut mortality. Now, your first thought here would be, oh my God, are there actually astronauts who smoked? I didn't think that was possible. It turns out there have been astronauts who smoked at least at the time of their selection. So again, the gold standard way to do this might be to get each individual smoking history and the pack years and when they started and when they quit and ages and all these good things and figure out their lifespans and what they died of and get this nice dose response curve of pack year history. But again, those data, if they exist, are going to be hard to get, and it would be nice to take a quick shot at this and see if it's worth doing. So imagine you're poking around the NASA Technical Report Server, and you find something like this. And this exists out there. You can go get it yourself, including the data set that underlies it. It was in the November 2001 Longitudinal Study of Astronaut Health newsletter. So this is the newsletter that the agency sends to the astronauts. It writes up little magazine-style features about health issues and reminds them to get screenings and to come back for health checks and all these good things. But what these data are showing us is 1 dot per selection class for astronauts. Those are those red squares. And it's the smoking prevalence of the different classes over time. Then the blue is LSAH comparisons. So these were drawn at a 3-to-1 ratio from civil servants to JSC. And then the green is the National Health Interview Survey. So general population comparisons. We've got all sorts of trend lines and R-squared values and things here. You can see pretty clearly, we have some information about astronaut smoking, and that it appears that they smoked more in the old days and that prevalence went down steadily over time. Turns out that what we really have here is 13 prevalence estimates, and not for all the classes, but from 1959 to 1996 with a couple of omissions for whatever reason. So the question becomes, can we use that to look at whether or not smoking among the astronauts has increased their mortality rates, again, from the likely candidates of CVD and cancer? Our explicit challenge is here that these data are prevalence data reported in the aggregate. We don't know who the individual smokers are, just from that 13 class prevalence chart there. Of course, again, confounding by indication, smoking is not something that's randomly assigned. All right, Mark Shellhammer, you'll have 2 packs a day, and Rob Ploutz-Snyder, you get 1 pack a day. No, people choose to smoke or not, and that may be related to other health behaviors and things that will eventually lead them to disease or not. That clearly sinking prevalence over time means that we're confounded by time period too. We can't just throw all these these astronaut selection classes in a basket and say smoking is the only thing that matters here, because they smoked less and less as we move forward in time. And we'll see a DAG here that actually talks about some of that. And of course, ubiquitous is our small n. This is less than the full astronaut cohort. 13 of these classes that are about 270 or so astronauts only out of the potential 350 that we have today. So what are some solutions here? Well, this time I have 3 for you. We can do a simple relative risk sensitivity sort of analysis. We can ask ourselves, who are the smokers among the dead? How many smokers were there among the dead? Next, we could do some simulation. And here we could take and try to do the gold standard study we wish we could do, which is all the lifetimes of the individual astronauts, take note of which class they're in and how many smokers were in their class, and then start randomly assigning smoking status, do our usual model and record the parameter estimate, and then do this many, many times and see what the distribution of that parameter looks like. And then finally, perhaps the simplest and most obvious thing would just be do a group level model where we analyze not individual astronaut lifetimes, but the 13 classes as our unit of analysis. And we'll see that. So if you're unfamiliar with relative risk, you're not an epidemiologist like myself, you can see it here in this 2x2 table. It's a very simple concept where we take the exposure and say you're exposed or not, and then you experience the outcome or not. We get these 4 cells where you exposed people who experienced or not, and non-exposed to experienced outcome or not. It's this A, B, C, D. So we could calculate the probability of dying if you're a smoker as A over A plus B, and the probability of dying as a non-smoker as C over C plus D. Our relative risk then is the ratio of those probabilities. So it really is a relative risk of smoking to not. So if we imagine that we took the 271 astronauts and took those classes that supplied us with at least 25 years of follow-up, what we would get is below the plot there. We would have 49 astronauts that could give us that much follow-up. Among them would be 11 smokers and 5 deaths from cardiovascular disease in this particular instance. We could say, all right, what if 0 of those deaths were from smokers? Well, then the risk is pretty much undefined because we don't have any comparison. All the deaths were smokers, then the risk sort of becomes infinite because, again, we don't have any deaths among non-smokers. So what we need to look at is these scenarios in between where 1 death, 2 deaths, 3 deaths, or 4 deaths are to smokers. And so we can very simply compute the relative risk if that were true, and you get these squares and little error bars on the plot there. And so if you still have an appetite for the null hypothesis statistical testing, you can draw that blue line that's at 1.0, and then these little tails, and there's my son in the background, everybody can wave to him. These little tails will, cross 1.0 or not, and you can feel like you're justified in declaring this is different enough from 1 to be considered something, or if you don't care, then you can just look at point values. What we see is that if only 1 smoker is among the dead, we get actually a slightly less than 1.0 relative risk, 0.82. If we see 2 or more, we start to get into positive territory, greater than 1. So we get about a 3 relative risk for 2 dead smokers, more than 5 with 3, and all the way up to about 13 and change with 4 dead smokers. So in this very simple way, yes, we're still confounded by a lot of things, but we see most of these scenarios suggest there's probably excess risk here. And of course, we could change this and say, maybe we only think 10 years of follow-up is important. That would inflate how many astronauts we have, probably tune down how many deaths we have, maybe increase the smokers. It's hard to know, but you could dial these parameters around and see different scenarios on this. It's of course important to note that I haven't published any of these data. Don't take this as canon. Don't run out to the press and say, oh, astronauts are dying of smoking. The point here is to show you the method, not the results. Next up is the simulation. So again, because we don't know the individual smoking status, we could just assemble the real data of lifetimes, start randomly assigning the smoking status, and then fit the model and do this over and over again. And we might get a curve that looks like this, where the red line's the median. Of course, our mean is probably somewhere near the peak of this curve. And we can run 10,000 of these, 100,000, however many you have the patience to let your computer crank out, with the thought being that the more you run, the more likely you are to capture the truth. So somewhere in between this log scale negative 1.5 and positive 1.5 is our truth. And you might say that's not particularly informative because that's somewhere between a 0.2 and a 4.5 relative risk, but it does put some bounds on it. And we see that even the median is not 0. It's small, but it's not 0. This thing isn't centered on 0. It leans a little bit more towards positive risk. And if we look at the mean of that curve there, it's actually a 0.02, which exponentiated becomes a mortality rate ratio of 1.02, or approximately a 2% increase in risk for each percentage, or not in this case, for being a smoker at baseline. Finally, the simple group model. Here I've thrown in a DAG to sort of help you think about what should you adjust for in this model, because now we're in more conventional territory, and we want to make sure that we're not adjusting for the wrong thing and creating bias, or failing to adjust for something that's an obvious confounder. So if we think about what we have available to us, we have smoking prevalence there on the bottom as the exposure of interest, the mortality rate is our outcome. We have that placeholder there called demographic factors. And that could represent a lot of things. Instead of drawing many, many circles that all have the exact same structure, I sort of group them into that placeholder of demographic factors. So you can think of that as age of the cohort that's male, what education level they have, if they were part of the military or not, these various factors that'll change with time, which is why there's a arrow showing that selection year is causal of all of these things, because we know that the smoking prevalence declined with time. We know they started to hire maybe more PhDs, fewer military people, more women, more minorities over time. And we know that in the general population, because of improving medical technology, the mortality rates went down over time, irrespective of who you are, because better treatments were available, early detection, things like this. So the general procedure here is take those prevalence data, which are at the group level, calculate some summary data for each of these classes and merge them together. So you would have the percent male in the class, the average age. Then we also want the number of people in the class and the person years. And so we can fit our model using those person years as an offset on a count model, and then we're directly estimating an average mortality rate for each class. What our DAG is showing us here is that all we need to do is adjust for selection year, and we've pretty much mopped up any confounding between the variables, at least the obvious stuff of being a common cause of both the outcome and the exposure. Doesn't mean we've gotten all the confounding, doesn't mean my DAG is right. There's a whole lot of ways this can still be wrong, but at least we can sort of move forward thinking, all right, here's my assumptions. Here's how I think the variables that I have are related to each other. And this is the best I can do at this moment. Still, the little disclaimer here, these are unpublished results. This whole smoking thing is still a work in progress. Here's what we get with these models. If we fit only a smoking term, we can see, wow, it looks like you're in real big trouble if you're a smoker. Because look at that, 16% and about 9% for cancer. But again, if we add that selection year, we can deconfound that and we see it reduces it by quite a bit. And that's that declining prevalence over time effect. So just with smoking and selection year in a model, it looks like about 5% and maybe 7% increased risk, which is pretty substantial, make no mistake. I have a note here, of course, that this is still likely confounded by this non-random exposure assignment issue. To really do this right, we should use propensity score type method to match control set and then evaluate against them against that instead of just kind of this dose responsive smoking in cohorts. So what would we conclude from these three different approaches here? I think that excess risks for smokers is certainly possible. It's nothing I'm going to rule out at this point. 3 out of the 4 simple relative risk scenarios suggest some increase in risk for the smokers. The simulation says this isn't centered on 0. There's potential for positive, greater than 1 mortality rate ratios here. And then the model, definitely when you try to start getting more specific and controlling for some confounders, says, yeah, there could be as much as 6 or 7% risk excess here. All of these things have the way that they could be wrong, but maybe we're triangulating on some truth here. And based on this, I'll probably at some point ask NASA, hey, can I get all those individual smoking statuses and do this the right way? Because I think there's something here that we need to see. And if that generated some excess risk, we want to know that and try to adjust for it in other analyses in the future, where we're looking at the radiation effect and its interaction with smoking, for example. All right, the third and final thing I'm going to bring you through today is international astronaut mortality. So in this one, we're taking a more conventional approach where we say, okay, NHST is pretty good for this because it's pretty bread and butter stuff. As of a couple of years ago, and I think these numbers still hold, there were 52 international partner astronauts. So these are the people who participate, the agencies who participate in the ISS with the US. That's Canadian Space Agency, European, and the Japanese Aerospace Exploration Agency, or JAXA. China has their own independent program, the 21 so-called taikonauts, Chinese astronauts. So I wonder, we see a healthy worker effect in US astronauts and in Russian and Soviet cosmonauts, where they are healthier than their general populations. Will we see that in these other groups as well? Challenge here is not so much like the others. We have the data, there's not many people, so there's a small n thing. The real challenge is that no one's died yet. So we can't really calculate a mortality rate, it's just 0. That means that our observed deaths and observed over expected SMR kind of calculation is 0. And that's not terribly informative to just say all the SMRs are 0, therefore they're fantastic. But what we can look at is that every day that goes by, the expected number of deaths under the general population mortality rate set would be increasing. So we can use that information to say, okay, if they're 0, that's fine, but how sure are we that 0 means anything? And how long would it be before we would become sure that it means anything under this sort of more conventional NHST P of 0.05, if you want, kind of approach? So what we can do then is look past that SMR of 1 kind of thing and say, we're going to accept that the SMRs are 0, and we're going to look at this person time accrual of expected deaths kind of thing and help us gauge where we are in this process. So when you do that, it looks a lot like this. The top row is using all causes of death for plots A and B, and it's comparing against the US general population, I believe. No, wait, it's column-wise for the comparison, so that A and B is all-cause mortality. C and D is only natural cause, but A and C are US general. B and D is against US astronauts. So what we're plotting here is the expected number of deaths in each of these agency cohorts over time. And that's going from when we picked them up through when we did the study, which was 2018. ESA is the solid black line there. And we see that they have the best shot so far of declaring any kind of conventional statistically significant quote unquote difference. If we look at all-cause mortality, they've actually surpassed the threshold there, which is about 3 deaths. And that 3 deaths comes from the computation of a 95% confidence interval in the usual SMR approach. What you do is compute the 95% confidence interval around the observed number of events, and then translate that to an SMR by using those endpoints over the expected. So when it turns out when you have 0 deaths, about 3 is where the expected is such that if you expect 3 and you have 0, that becomes a significant 0, if you will. So we can see that ESA passes it in that they haven't died in any plane crashes, car crashes, spacecraft accidents, or anything like that. They beat both the general population and US astronauts in that respect. But if we take away, again, those sort of lightning strikes that could happen to anyone and look only at disease process, we see that all of those cohorts have a long ways to go before they're declared to be really much better than their general population, and maybe not quite as far to go before they're declared better than US astronauts. So that's kind of interesting in itself to me, because we know, yes, their general populations are pretty low, at least in comparison to the US and certainly in comparison to Russia. But I didn't realize going into this that astronauts were, the gap there between astronauts and these other agencies is not quite as great as it is between these other agencies and their general population. One of the nice things about this then is that if we want to go forward looking, we can make statements like I've excerpted out of the article here. We were discussing this idea that Japan has very low general population rates, and it would be difficult to see a healthy worker effect there because you have to go really, really low before you could see this difference. This Japanese general population is pretty low to begin with. So this is just a statement where we were saying we could look ahead and sort of pre-calculate. And essentially what it's telling us is that if all these Japanese astronauts continued to live and no one died, once they got to 2035, that's when we'd finally say, okay, there's enough of a gap here between the Japanese general population and no dead Japanese astronauts that we're pretty sure they're even healthier than the general population of Japan, which is really saying something. Of course, we could do that for any of the cohorts. And we could also say, what if 1 person died by 2035? And what if 2 people died? So again, play scenarios and what ifs. So the conclusions from this little exercise is that enough time has passed to say that in terms of a conventional sort of NHST analysis, that ESA astronauts are at lower mortality risk from all cause, but we're not so sure about the disease process, the natural causes. And one thing we can note here is that this is probably true even if we did, as Rob suggests, trying a one-sided hypothesis. I didn't, for the article, do that, but if you calculate that threshold value saying they can only be worse or no different, then you could obviously lower that 3.0 threshold or raise it actually, and then sooner in time declare that they're better off. All right, so bringing this all home here. NHST is a prison of the mind simply because the dogmatic application of it leads you to distort your studies and you lose opportunities to learn from your data. And that's really what we need to have our goal be. And that's kind of the motto of data science, is learn from data. So rather than falsify or support hypotheses, let's pivot our brain to think about we want to learn from data. And the solutions include thinking about the context and the implications of your question, exploiting the data to try to answer some aspect of that. In the examples I provided, certainly there's no definitive answers there. And people could argue with me and say, I don't believe it. But that's good. That's what I want. I want to inspire some conversation around these tough questions and say, all right, if you don't believe it, what is it about the evidence that I supplied that doesn't convince you? Or what evidence would you want to see that would? And that's the fruitful ground from which we design the next phase of studies, the follow-on science that will maybe get us the answers we want. We have to know that we're going to make mistakes. With or without NHST, you're going to get it wrong sometimes, but that's okay. There's never going to be a situation where the fate of the world hinges on your one study, and you're going to turn in your results and NASA's going to completely cancel the Mars missions because you found that one thing. Other people are going to replicate it. We're going to look at data from other situations, from the analogs, from other missions. We're going to try to see if what you said makes sense in the broader context, and other people are going to try to see if it's true. So don't be afraid to make some mistakes and to stimulate some conversation. And it's kind of in line with, I guess, the ASA thing is be creative, be reasonable, and be passionate. Understand the context of your data, really dig in, understand what it's trying to tell you, and always keep the broader context in mind about what do we know about this headed into it, what do we really expect to see, does the result make sense? If you're interested in more commentary along these lines, there's a little chapter that is a commentary chapter that Mark Shellhammer and I wrote for this open source book called Beyond LEO, Human Health Issues for Deep Space Exploration. The link to it's right here on this slide, and it's completely an open source book, so you can download this chapter or others completely for free at this InTech Open website. And then you can really throw some rotten tomatoes at us when you see the full spectrum of our views on this. If you liked what you hear and you want to talk about it more, or you didn't like what you hear and you want to, complain at me, feel free to message or connect with me on LinkedIn, and I'm happy to have those conversations. And so with that, I'm going to turn it back over to our MCs here so we can do our Q&A portion of the symposium. Thank you for your time.
Very good. Thank you, Rob. I appreciate that. Great. Before you go away, I'm going to ask you a question. Before I ask you a question, though, I'm going to remind people watching online, which I guess is everybody, that you can enter questions into the chat box, and Nabila and a band of like-minded individuals behind the scenes will sort through them and triage them, and we'll get the good ones out there. So start asking away. If we don't get to all of the written questions before we are finished in 44 minutes, then we may be able to prevail upon the speakers to answer them in writing, and we will post them in a conspicuous place on a Hopkins website, which we did at the last symposium. But now, Rob, the question I have for you, I'm having a little bit of a difficulty properly phrasing it, but maybe you can help make sense of the question before you answer it. But I think you were referring to in the ESA astronaut population specifically, but let's talk more broadly. In a small population in general, there's kind of a lack of what I'll call lightning bolt events. I think you mentioned car accidents, aircraft accidents, spacecraft mishaps, variety of things like that, that the proportion of them occurring to that population might in fact be the same as the proportion that would happen in a larger population like the NASA astronaut population, but the sample space is not adequately explored, because it'd be like playing poker and you can figure out the statistics, the probability, likelihood of a variety of different poker hands. But if you only play for 5 minutes, you're not going to get the very, very rare hands. So the statistics of extreme events, of highly unusual events, is that inherent in your analysis? Is it something you have to consciously, explicitly be aware of? Does the question make sense to you?
I think so. You're talking about the hand you could get versus the hand you've been dealt. And that's really what we're trying to investigate in all these kind of mortality analyses. What we're seeing there is that if you assume that they're truly at the same risk as the rest of the population of having car crashes and spacecraft mishaps and dying by suicide or murder or anything that's not a disease process, then the ESA people have already seen enough of a deficit of those sort of things to make you believe that they're actually not at the same risk. Now, philosophically, you could say, maybe that's true, or you could just say, yeah, it's the hand they've been dealt. And that's where adding more ESA astronauts in the next 100 years and watching them for the next 150 is going to really help you decide if you believe that's true. But then again, that could be a changing phenomenon too. It could be temporally confounded. There could have been a golden period of ESA astronautics where they didn't die of anything external, but then all of a sudden you've got something changed, and now the parameter's different, and they're crashing cars and crashing jets and doing crazy things that put them at high risk. So the mortality of these astronauts over time is a very tricky thing to look at. And the best we can come up with so far is just to say, all right, let's benchmark it against something known and see the hand they've been dealt. The hand that they're actually playing against that they could have got is what you're.
Yeah, it's kind of like the black swan event in some ways, right? In some of these cases, the occurrence rate is so low. How can you say something systematic about it? But that's a typical statistician's answer, which is I just wanted the right approach to be able to look at the right test, and you gave me the right way to look at the question. So it
Glad
drives
to be
me
of
crazy,
service.
but in fact, that's the better answer. Okay, so now what I'm going to do, I have a couple of questions on as backups here that I'm ready to go to. First, though, I want to, before we open it to questions to anyone, I want to see if either of the Robs have anything that they might want to address to each other, a question or a point that one of them brought up that the other would like to pursue.
Yeah, I'll go ahead and just make a comment, not necessarily a question, but I think it's good for the audience to know that while Rob and I, we, communicated in preparation for this talk today, we basically just decided, well, who's going to talk first? And it was decided that I would go first and then lead into Dr. Reynolds' talk. Because it seemed to make sense. I was sort of setting the stage that, the old hypothesis testing paradigm's got a lot of flaws. I tried to come up with some approaches that if you're still sold on doing those techniques, here's some ways to maybe describe your results differently, focus on data differently. And then Dr. Reynolds took it even another step further. So I wanted the audience to recognize that we didn't really collaborate on these two presentations. I basically set a stage, and then he followed with what I think are some really creative approaches to data. But in commenting to that, so this is the first time that I've seen his talk, and I really like the way, Rob, the way you're taking severely limited data and phrasing a question that we can ask of that data in a logical way. And even if the answer to that question's imperfect, it gets us on a right track. And I think that's the kind of knowledge HRP, the Human Research Program, needs. They need to know, are we on the right track? And then regularly, check back and say, are we still on the right track given today's data and 10 years from now, and so on. So so mostly I'm sort of appreciating the approaches that Rob, that you presented to us, because it's right in line with what ASA is trying to advocate for, being really thoughtful, being creative, accepting uncertainty, and then communicating what you can from limited data. So more of a comment, I guess, than a question.
Yeah, thanks.
Yeah, thanks for that, Rob. And I would add that this is in line with my own personal philosophy of all data are good for something. So yes, you may not be able to answer all the questions you'd like to answer, but you can look at what you have in your hand and say, what might this tell me? And that's the approach I try to take. Secondarily, I also want to point out something that I didn't say that I should have said, which is I haven't completely thrown out null hypothesis statistical testing. I do still find it useful. It's one of the tools in the toolbox. It's just not the only thing I do, and it's not the main driver. So you can free yourself of the prison of the mind, but it doesn't mean you have to completely walk away from it. Just don't be in the cell.
Yeah, so actually, Rob Reynolds, what you just said, I think is a really compelling point. All data can tell you something, and yet, if you adhere strictly to what the statistics books try to tell you, they say, if I'm understanding them correctly, that what you said is in fact not fair, not correct, that you're supposed to design your study, figure out how many subjects, how many data points do you need based on a power analysis, effect size that you're looking for, et cetera, et cetera. Do the experiment. Don't you dare look at the data values and do statistical tests until the very end when you've acquired that number of data points that you preordained. Then do your statistics test, positive or negative, significant or not, and then you're done. No, you're not allowed to go back and reanalyze the data, because now you're on a fishing expedition and now you're in the domain of trying to make something of nothing. And that in my impression is a strict reading of statistical rules, that you design the study with all these things in place, and then you're done. If it didn't give you what you thought, you rejected the null hypothesis or accepted it, but you're not allowed to go back and wring more information out of the data because that's not the way you designed the experiment to get additional information out of the data? First, am I misconstruing what those conventional statistics books have said? And second, what do you have to say about that?
Well, I think that goes back to your earlier question after Rob's presentation about how did this happen? How did we get to this place? I don't know if it was Fisher or people after Fisher, but it became a cultural issue of like, this is the only valid way to do this. And if you're not doing this, you're being sloppy. And that just feeds upon itself until it comes down to there's that culture of authority around it where you need to do this or you're a joker. And then I think there's the other side of the coin where it's like, if I just do this, I can be done with the stats part and I can move on, as you suggested. Like it becomes a wise checklist where you can just hit all those boxes. You got to p-value, you're good to go. Let's get the next grant. Let's write the paper. And so freeing yourself becomes a matter of saying that isn't enough and need to wring everything we can out of the data and really understand everything that we might learn from it before we're ready to move on. So I don't know if that answers your question, but that hopefully adds to the context of the discussion.
I'll comment too. I think, Mark, like me, you're a prospective experimental design person, right? Yeah. I think we both kind of gravitate towards that type of research where you design a study, it's prospective, you decide what outcomes you're going to collect, what are important covariates to consider. You do randomization if that's possible. You collect your data, you analyze your data according to the aims and hypotheses that you wrote up. And I do think that that's that needs to be done in order to sort of safeguard, in particular, grant dollars, right? That big reviewers are coming together. There's too many good ideas, and so they have to decide which ones are worth tax dollars to pay for. And so when they do that, there is sort of an obligation to do what you said you were going to do. After that point, though, I would take issue with that. We can't go back and look at the data in other ways. And in fact, I don't know a single investigator who says, okay, I'm all done, next grant, right? They all go back and look at it again. But also, today there's all kinds of data that are just already existing, waiting for people to work on. Not just, Dr. Reynolds was talking about data from the LSAH at NASA. So astronaut data that's been collected over the years if you're a NASA researcher. But there are national data sets on virtually any big topic today: cancer, drug and alcohol addiction, just daily living, cardiovascular disease, diabetes. There's lots and lots of these large national data sets ready for you to start analyzing. That's a different animal. For that, we have to take a different statistical approach too. We didn't have the luxury, for instance, to collect the data exactly that we wanted. And so right away, going into those types of studies, you recognize, hey, there's going to be limitations with what I can use. And so there's going to be limitations with the kinds of conclusions I can make too. But again, accepting uncertainty and accepting those limitations will get you a lot further along in sort of broadly answering the questions, even if it's not the sort of the precision level that you wanted or that you would have designed yourself.
Okay, I'll accept that. By mentioning precision, this will be my final question for now, and then we'll turn it over to Nabila for audience questions. But Rob, you mentioned the magic word precision, and you and I talked about precision quite a bit when we were talking about putting together plans for NASA one-year missions and things like that based on existing data sets. But it brings to mind the issue that, I want to say this tactfully, maybe not all experimental questions are equally important, and therefore the statistical design should recognize that. So let me give an example. At the risk of antagonizing any of my discipline-specific friends out there, if you're on a 3-year mission to Mars and you have a cardiovascular event, a heart attack, well, that's bad news in anybody's book, right? That's just really, really bad. So you want to figure out if there's an experimental design or something that's looking at that problem. You would want to give that a high priority. It's like if you're still willing to do a significance test it's like you would give additional significance to that significance test, if that makes sense, because it's a really important thing. If, on the other hand, you could say, again, at the risk of antagonizing people, bone integrity and muscle loss, serious problems. You don't want to be cavalier about those, but you could say, all right, but there's a backup for those. You get to Mars, you're going to wear an exoskeleton, or you're going to have additional padding or stiffness in the suit. We can compensate for reduced muscle and bone capacity, but we can't compensate if you have a heart attack. So you could say that there's, maybe there's a continuum of, I don't want to say importance, but the level of concern that you would give to questions. Are there statistical techniques that would allow you to incorporate that type of thinking into the analysis?
Wow, it's a great question, Mark. One of the things that comes to mind, again, is challenging the defaults. If you wanted to go the null hypothesis testing approach, which we're all pretty well schooled in, I would suggest at the outset that you absolutely have to challenge the sort of default assumptions that everybody goes with. In other words, you'd want your experiment to be highly sensitive to a possible cardiovascular event at the risk of calling an event likely when it's not that likely, just because maybe there's an intervention space that you could get in and prevent that, or at least address it early on. I think it's also sort of above my pay grade and more to the NASA sort of science management, where, and I think they do this to an extent, where the calls for research are prioritizing those things that are sort of mission critical versus, yeah, I'm not so good, but the mission still lives, the astronaut still lives, and we're not bringing back a spacecraft with bodies, we're bringing back living, breathing people. So I think it's a mix, right? It's a mix of what research you fund, because it's the most important critical stuff that saves or keeps people alive. And then, yeah, there are, I think, ways to design your statistical approaches to data that balance your different types of errors more appropriately than just, everyone else does 0.05, so I'm going to do 0.05. Yeah, everybody does two-tailed tests, so that's what I'm going to do too.
If I could jump in on this one, Mark.
Sure.
To me, what you're describing is somehow trying to weight by consequence of different
Yes.
possibilities.
Yes.
So what you're really talking about then is kind of expected values, where you have a likelihood and a consequence, and that gives you some sort of cost function, if you will. So ideally, I think this is why we're doing DAGs at HSRB. For people who aren't familiar with this, at the Human System Risk Board at NASA, we've been undertaking this project for the last 18 months and trying to draw 30 different directed acyclic graphs that we're going to knit together into one gigantic directed acyclic graph that will allow us to try to start quantifying where different factors in the spaceflight environment make contributions to both the likelihood and the consequence of different mission outcomes. So to me, that's the approach I would take, is to try to, even if you're somewhat wrong, at least try to get some relative ranking of different factors and what the consequence will be of leaving them unchecked or modifying them in some way, based on how they contribute to the things you care about in the end, like bringing people back alive.
Yeah, actually, you both have touched on what it led me to think of the question in the first place, which was that when I was working with Rob Ploutz-Snyder 7-8 years ago now on figuring out more of a master plan for HRP to prioritize research that you would want to do on additional one-year missions. This was part of the thinking that was going into that. How many one-year missions are you going to do? Even ideally, not very many of them. So then you have to say, well, what are the most important questions that really need to be addressed, and to what level of precision and certainty do we need to address them? Well, the ones of higher consequence maybe should get more resources. So Rob Ploutz-Snyder, you said it exactly. You said that's kind of more of a program management type of question. Precisely. That's where that's coming from. Okay, thank you both for your comments on that. So I think I've spoken enough. I'm going to turn it over to Nabila to see if we have anything from the audience.
Of course. So first of all, Dr. Ploutz-Snyder and Dr. Reynolds, thank you for your excellent presentations. We've gotten several audience questions. So to begin with, should all research groups just plan to have a biostatistician on their team?
I'll say yes. I think that would be phenomenal. And in fact, not only that, but bring them on when you're starting to design your studies, because that's when we can have the most impact. Try not to bring them on at the end. Having said that, I recognize that, all research is expensive. And so for you to get somebody to fully engage, and the way I operate my shop, by the way, is that, I think that your biostatistician, your operation should have them on faculty types of appointments, not staff so much, because they're everyone's in it for the same game, right? We're all in it to make science work, to get publications out. And so if you're able to get biostat faculty to collaborate with you, that's going to be really beneficial, because they're in it for the same reason the content experts are in it. So I would say, yes, that would be a phenomenal idea. Get them in early, promise a percent effort that's sort of in line with how big the analytic part of the project is. I'm on some grants for 20% FTE. I'm on other grants for a mere 5% FTE. And it just depends on how engaged I need to be throughout the whole study. I don't think everyone does this, but I do think it increases your likelihood of getting, good science done. Also, your likelihood of getting funded. A lot of times people come to my shop saying, yeah, my grant didn't get funded, and one of the reviewers said, you need a statistician on board. It's getting to be more recognized. So I would say unequivocally, yes, though I'm sure there are grants that don't require a statistician.
I think it's kind of funny to ask two biostatisticians if you need a biostatistician, because of course we're both going to say yes. And it would be helpful, but I would also point out that that does not absolve you as PI of thinking about things in the way we've told you today, and thinking differently about your hypotheses and the questions you ask. That's part of our problem, is that we try to outsource the whole statistics thing because it's just hard to think about and it's complicated, and we don't have the training for that. And that's all fine. You can rely on the biostatistician to do the heavy math lifting, but still think about, am I asking the right question, and what is the context, and what do I already know, and what do I expect to see, and what else might we learn?
Yeah, and then I guess I'll piggyback one more on that, is listen to what they have to say, because it's not something that you're doing to check the box like the power analysis. You're doing it because you really want their input to make your science better, and they're going to think things through very carefully, as long as you give them the time to think them through very carefully. If you come a week before the deadline, then don't expect much.
Yeah, so this actually reminds me a little bit of the case when I was in graduate school, and I did go to a statistician too late. But okay, in my defense, I was a young graduate student, but nevertheless, we were fortunate that we had a statistician on the staff of the laboratory. His name was Alan Natapoff, and he's still there at MIT. Worked very closely with Larry Young for a long, long time. But I do remember the first time I went into him with spaceflight data. It was a done deal. We already got the data. I didn't know enough to go in ahead of time. Plus, the experiment had already been cast in concrete before I even came along. So I had what I had. But I do remember going into him and just asking him, what's the right statistical test for this? Classic, stupid question. And he said, tell me about the experiment. Describe to me the experiment. And I thought, I just want an answer. Just tell me what test to do. I don't want to go through. But of course, he was exactly right. And hence started basically a weekly meeting for months and months, in which he really came to understand the science of it and advised me on, say, unorthodox or unusual statistical approaches that I would not have considered, and he would not have suggested if he didn't understand the science and the experiment. So imagine what would have happened if he had been involved earlier in the design stage. So I'm all for that idea of including statisticians, because they help you think about the experiment design, not just the statistics.
All right, thanks. So for our next question from Jack M, he wants to know, could you talk a little bit more about the use of machine learning? How has that impacted the statistics field, given that it relies so heavily on statistics itself?
I guess that one's probably aimed mostly at me, but it's kind of amusing the way this has all unfolded over the last 10 years or so. Because as machine learning gained a lot of prominence and started getting attention, I can remember very palpably, and I'm sure Rob remembers this too, the ASA writing these editorials saying, wait a minute, aren't we machine learning? Aren't we data science? And they were genuinely perplexed at how there was any difference in what data science was proposing from what statistics was already doing. But what it comes down to is the use of more algorithmic approaches and actually not caring at all about inference. Most often people are using machine learning algorithms, at least the supervised methods. They're labeling outcomes and then saying, here, machine learning algorithm, be able to reliably tell me which is going to be an outcome and which isn't. There's a big focus on prediction and not caring about the data generating mechanism per se or how it all works, just being able to accurately make a call. And that's very useful in business because maybe the thing you're trying to change isn't really dependent on why it's that way. You just want to talk about what it is. And so you want to find, and I can give you an example from healthcare, working in health insurance companies. Most large insurers have a staff of nurses that they employ that do outreach with members. And so if you have diabetes, they're going to try to enroll you in a program with these nurses where the nurses call you up and say, hey, how are you feeling? Are you checking your blood sugar? Have you been to the doctor? How are your feet? And they're trying to prevent you from getting worse. But the big problem the insurers have is who is it worth spending those resources on? Because they're precious. You're paying a nurse to work the phone bank. So they're trying to predict who's going to have these diabetic complications in the next couple of years, knowing that we only insure people for maybe an average of 3.5 years before they change jobs or something. Who do we need to work with in that short span right now to prevent them from getting worse? So you bring the machine learning in, feed it everything you know about the patients and their utilization, and any records you can get from their doctors, and you say, all right, these are the likely candidates the nurses should be calling. You could take it a step further and say, we don't want to call them all because there's too many. Who's likely to actually participate and see benefit? And so again, you don't really care why, you just want to know who's the right person to call. So that's been the big, I think, difference in the development of machine learning versus traditional statistics. Obviously, the meat of it is that the machine learning just thrives on more information, more information. The more you can give it, the better it does. And that's why we don't use so much of it, the deep learning kind of things in investigating human health in spaceflight. But there's been some symposia at the Ames Research Facility over the last year and a half, where they're talking about where are the places that this deep learning and these convolutional neural nets and all these sorts of things would be useful inside a spacecraft. And that might be related to making predictions about who's going to suffer a problem based on what vitals we can collect off them in flight and things like that. That, of course, would be trained on non-spaceflight data. So you see that there's always a use for these things coming in from the peripheral. It just won't be trained on spaceflight data exclusively. There'll be some version of transfer learning there. Now, what I've done and how it's changed my research, I teased about this, about the unsupervised methods. If you have some noisy data and you're trying to, let's say you have a variable you want to use as a covariate in a model. And as Rob says, check your assumptions. And this thing, it's just sloppy and it's not going to be a good continuous variable, so you want to discretize it. You might use k-means clustering to come up with some groups that minimize within group variance and maximize between group variance, instead of a more traditional approach like just use quartiles or something. Because there you use quartiles, you're saying, all right, I want equal spans of range, or I want equal ends in the group as close as I can get. And that may not make any sense when in reality you're looking for kind of that signal of, is there some kind of dose response relationship between this variable and the outcome? Then concentrating people into small groups where they're very similar to each other is a better way to do it. So it's little tricks like that. There's a project Mark and I are involved with in Colorado where we're bringing a lot of psychometrics into it because we're trying to look at various physiological measures that have a lot of correlation in them. So we need to somehow decorrelate those and find the unique signal across all these different variables they've measured. And so we can use things like principal components analysis or factor analysis to try to boil those down to the essentials. So I hope that gives some flavor and answers the question to everyone's satisfaction. If not, please put more in and we can elaborate. Rob, you got anything on this score?
No, I think you covered it pretty well. The only thing I guess I would add, because I do, a lot of statisticians, as you said, when this sort of first came out, kind of looked almost with I guess I wouldn't say disgust, but at least a lot of pause and question about just letting the algorithms do work without any theoretical guidance. I think that's there's still a bit of that opinion. But what comes to mind for me is something that I called shrinkage, right? When you have your current data set and you're building algorithms unsupervised to predict some outcome or another outcome or who's going to benefit or not, it's going to work really well with that data set because it's built around that data set. But to the extent that you can then say, well, this is also going to work for another data set, there's always going to be some R shrinkage, some reduced capacity for it to work outside of that one sample. Now that we have giant data sets available to us, the extent to which that happens is probably a lot less, but it is something to be aware of. You're basically capitalizing on the variance and covariances in your current data set, and that relationship may not exist outside of that data set, at least not as strong, perhaps.
So Rob, what you were talking about the statisticians showing some consternation about, hey, this is what we've been doing all along, machine learning, deep learning, whatever. So it reminds me of a conversation I was having with somebody who teaches machine learning and deep learning a few years ago. And she said she could tell when her students finally grasped the essence, the aha moment, because the thing that she was trying to convey is all these fancy techniques, they're just statistics. Now, that's not to denigrate statistics, but it's not magic. It's not something fundamentally different. And she said, when I saw their faces drop in disappointment, then I knew that they had gotten that message. It's just statistics.
Yeah, and a lot of the things that people attack about machine learning are actually happening under the hood of their favorite statistical program to solve linear regression anyways. It's very rare that they're doing the matrix algebra in complex models. They're doing Newton-Raphson things, which are the same idea. They're searching the solution space, trying to find local minima and maxima. So it's really not that different in the end, other than, whether it thrives in a large or small data environment.
Right. Right. Changing it quantitatively doesn't necessarily change it qualitatively.
We've also gotten a lot of interest from the audience regarding communication of statistics and ways to properly teach statistics and statistical methods. So from Janine, we have a question. What strategies do you use to communicate complex statistical analysis to non-technical audiences?
Oh, you probably watched me fail at that today. I try to explain things in the most straightforward conceptual way that I can, always tying it back to what we're really talking about and what's really happening. So again, it's thinking about that idea of a data generating mechanism. Why do the data look like they look like is what you're trying to answer. What gave rise to this data set? And if you can talk in those terms rather than technical jargon about p-values and standard errors and things, I think that communicates at least the ideas better. Now, if you want people to understand the complex technicals, then I've never been a statistics teacher, and I turn that one over to the other Rob.
Yeah, it's tricky. There are all kind of different learners. There are visual learners. There are people that love tables and figures, and that kind of resonates with them. And then there's others that really like to look at numbers and they can see patterns in numbers that others can't. So a part of it is sort of connecting with your audience and where they're at. I found generally, though, that bringing a lot of examples is the way to go. In fact, when people ask me, and I get this question a lot, what's a good stats book I should get? And my next question to them is, well, what discipline are you in? Because most disciplines teach some level of statistics within that discipline. And that's not to say that whatever that discipline is doing a phenomenal job of teaching statistics, but chances are really good that those textbooks have examples that those people can relate to. So if you're coming up in the social sciences, they're going to have examples that are social science relevant. If you're a business person trying to learn statistics, there are great business examples in those textbooks. If you don't get that knowledge, I will say the social science examples, most people tend to kind of like. And so I will use those a lot. There's some sort of intuitive gravity of those scenarios where, the content area is interesting enough to hook you in. And then you can maybe show some examples of how this or that statistical technique might be useful in those areas. So a lot of examples. I do tend to use a lot of visualizations. I slow way down. I know I talk fast during my presentation, but when I'm explaining stats, I try to slow myself way down and bring in lots of examples.
All right. Along similar lines, we have a question from Michael Zero, who asks, p-value tests are taught as a fundamental component of statistics, starting even during the high school curriculum. So should fundamental courses be restructured, or are there considerations you discussed about p-values that may be more appropriate for advanced coursework?
There are a lot of people who would say that we should start over. If you talk to some Bayesian folks, they'll tell you that's where we should start. We should be teaching Bayesian statistics first, and then maybe go into frequentist approach or not, depending on how diehard they are in the Bayesian world. I didn't learn Bayesian until after I was sort of fundamentally rooted in frequentist statistics, so the p-value area. It's a hard thing to say. I can tell you that as I've taught biostatistics over the years, it used to be, like most biostats classes, they start off with several chapters on different types of data descriptive statistics, and then you start going in one chapter at a time on this or that statistic. And what in biostats worlds, what I'm seeing is now within every one of those chapters, there's sections on, well, it started out on power and effect size. And now it's getting more into characterizing the magnitude of effects. So embedded within that chapter on this test or that type of test are those little small sections dedicated to how do we characterize, how do we describe the effect magnitude. So we're starting to see that now. The ASA really is coming down hard on p-values, and I agree that we've relied on them way too much, but I'm not ready to throw the baby out with the bathwater. I still think there's a lot of information there. It's just that we can't become lazy about it. We have to think very carefully about it. I don't know, Rob, you might have another opinion on how we should be teaching the youth as they become.
Yeah, graduate school is a funny thing because it's really modeled on the medieval apprenticeship, and yet we've tried to industrialize it over the last 100 years by having all these courses and units we have to complete and all this. The best way to learn this stuff is to work with someone who does it this way and figure out what's important and what you should look at and learn through immersion. I think if I had to stick to the current course model, yeah, I'd probably start with Bayesian because that's how we all think anyway. We have some preconceived notion about what reality is, and then contact with reality either confirms or denies that for us. And that pretty much goes with. It takes a little bit of mental gymnastics, I think, to become a frequentist and to get your head around this NHST stuff, which is why so many people get it wrong and have all these erroneous assumptions that you outlined in your talk, is that it's not an intuitive thing. You really have to sort of twist your mind into a weird shape to understand the logic of it. So it should not probably be the central focus of most courses, but kind of one of these exercises you can do to eliminate the possibility of sampling error, right? Piece of the puzzle in your overall epistemological quest for truth.
Of course, so continuing on with this interest in p-value, are there situations in which you would say a p-value is still more useful than other measures?
More useful, I would probably say no. I think the most important issue is if we have an effect, whatever it is, a group difference or a predictor that is relevant in understanding an outcome. There's so many different ways to say what is your effect. I think the measure of how big that effect is and what that means is probably more important. And when we talk about the confidence or compatibility indices, I always encourage people not to just report them, but to phrase your conversation around, if the effect is as small as the lower boundary of this confidence interval, this is what it means clinically. Now, if it's as big as the upper boundary, this is what it means clinically. And so if you are somewhere in that space where it's important to you that, wow, I'd really like to have that kind of a response, well, then you know that this predictor or this treatment was a useful thing. And if we, instead of focusing on a parameter as if that's the one, we focus on this, uncertainty of what the parameter truly is, but we think it's somewhere between here and here. And then we take that one step further and say, well, if it's this small, this is what it means. But if it's this big, this is what it means. I think that's where you give people context to sort of appreciate your data.
Yeah, to me, it's been given too much importance because it's answering one very narrow question, which is how likely am I to see this ratio of parameter to standard error under the null? And that's just eliminating one way you could have got it wrong. So you should spend more time thinking about all the other ways you got it wrong instead of that little narrow one. I don't think it's ever more important than other measures, no.
All right, so this will be the last question that I think we'll have time for. But otherwise, if all data is valuable data, what is the minimum n to which you can get any useful findings? Can it be 1?
Well, given people are doing N of 1 studies, then clearly 0 is not helpful, but 1 can be. I think the context of N equals 1 is normally in the personalized medicine sort of realm where we're looking at how does this individual respond. So if I send him to Mars, what should I expect for him or her? But I think there's value there in that you can establish what's possible. You can't, if something happens one time, you can say, well, we know it's not ever going to be never. It's at least happened once, and we should try to determine if it could happen again. So it's, again, hypothesis generation and bounding the possible.
Yeah, sort of piggybacking on that, we're all familiar, I think, at least with the idea of precision medicine. That is, when you go to talk to your cardiologist or your family physician or whoever it is that you're talking to today, you want them to treat you, your problem, given your background. You don't want them to treat the average person that's like you. So when I go to my doctor, I don't want him to treat the average bald guy that's in his 50s. I want him to treat Rob Ploutz-Snyder, right? And the statistics is kind of, unfortunately, historically not been about individuals. It's been about the average, the mean, the average person in this or that category. The N of 1 experimental design is one I think that's worth taking a look at for folks. I think it's titled improperly. It really should be called N of 1 at a time, because that's what it is. But it's like a precision medicine approach to collecting data, let's say on a treatment longitudinally over time. Now, there are some requirements where it has to be the kind of data where you can collect it frequently and continue to get touch points where you're evaluating how the patient's doing, or the astronaut in this case, given the current treatment. And if they're not doing well enough, then we might up or down the treatment. So thinking in astronaut health longitudinally, they're in a microgravity environment. We take some measurements of their muscles and their bones and the neural outcomes periodically. And if they're not doing well, or they start to go in a pattern that we don't like, we might increase their interventions, say exercise, or if we're gonna give them a pill to help bone demineralization, we might increase the dosage. So it's no longer a standardized protocol that we're going to randomize people to receive the same treatment, measure them repeatedly, and then describe the average. We're going to give people what they need as they're going. And then when they're all done, we're going to characterize that N of 1. But then we're going to do that for lots and lots of people. And the way you analyze that data is just the way you would analyze a meta-analysis, where in a meta-analysis, you're collating data collected from multiple labs across the country or the world with some certain study criteria that have to be met in order for them to be considered in your meta-analysis. Then you're creating these forest plots that show what are the effects in Mark's lab and in Rob's lab and in my lab and in your lab. And then we try to get an average effect. This is exactly what N of 1 studies do, but each study is actually a person. And so some people are going to be more responsive to the treatment than others. And each person got a treatment that's titrated specifically for them. And so in that way, we get a sort of optimal effect, like this is how good it could be if we optimize the treatment for you as an astronaut. I kind of like that approach. Having said that, it's really hard to find a research study where I can actually apply that. I'm looking for options for that all the time, but it does require these frequent touch points, typically that the subject themselves can measure, evaluate, and respond to. Otherwise it's super time intensive from the PI team. But those are the kinds of ideas I think that get us closer to precision science as opposed to precision medicine.
Okay, thank you. I'll take it from there. Nabila, thank you for moderating question and answer. Malika and Linda in the background, thank you for helping out with this. The Hopkins at Home people, but especially thanks to Rob and Rob. Really enjoyed this. The time, as usual, went really quickly. If we have additional written questions, we may prevail upon you guys to write something up and post them. Who knows, maybe we'll do a round 2 on the topic of statistical data analysis approaches, which brings up the point that if those in the audience, those watching, have particular topics that they might want us to explore in the similar format, we do this every 3 to 4 months so far. Let us know, get in touch with us. Variety of contact mechanisms available on the website. So again, thank you. Thank you to our speakers. Thanks to everybody who participated. Thanks to everybody online. And hopefully we'll see everybody in another couple of months. Thank you.